Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin, and I'll be running through part 1 of problem set 14, molecular shape and VSEPR. Okay, VSEPR is the theory that we use to determine molecular shape, and it stands for valence shell electron pair repulsion. Okay, valence shell meaning we're looking at the electrons in the valence shell. Okay, and that the electron pairs, remember they're always in pairs. They're either in lone pairs or they're in bonds. Okay, either way, that's a pair, and it's repulsion. They're repelling each other. Remember that electrons are negatively charged, and when a negative comes close to a negative, they like to repel each other. Okay, like repels like, whereas opposites attract. Right. So when you'll kind of see how we use this theory when we're looking at these kinds of shapes, because if you look at, let's say, this balloon, and this balloon, when you try to tighten balloons like that really close together, they try to push each other as far away from one another as possible to give them their own space, right? Same idea, except we're treating them as we're treating these balloons or the electrons as kind of balloons in a sense. And so you'll kind of notice that they'll end up getting really far apart as they can as possible, because they're repelling one another. And that's where we get these shapes. So number 1 says, once you know the concept of the bond dipoles and molecular shape, you can determine whether a molecule is polar or nonpolar. Now they want us to draw the Lewis structure, okay, and draw the dipole arrows to show the bond polarity. Okay, that's going to be different. We have bond polarity and molecule polarity. So for any molecules that are polar, draw a dipole arrow to show the direction of the molecule's polarity. Okay, so we need to draw dipole arrows for bond polarity, and then later, if the molecule is polar, then we can draw the dipole arrows for the whole molecule. So I'm going to draw the Lewis structure, but I'm not going to go through all the steps of drawing the correct Lewis structure. We've done that in like 4 previous videos. So if you need help drawing a Lewis structure, I would refer you to those videos. But here I'm just going to draw the Lewis structure, the correct Lewis structure, and then we're going to determine whether the bonds are polar and whether the molecule is polar. So to determine whether bonds are polar, you need to use an electronegativity chart, which I've included down here. Okay, remember, in order to have a polar bond, the difference in electronegativity, let me actually write it over here. Okay, difference in electronegativity has to be between 0.4 and 2.0, okay, in order to be polar. So I'm going to put polar. And remember that below 0.4 would be nonpolar, and above 2.0 would be an ionic bond, okay? So this is what we're going to do. So I'm going to look at boron here and chlorine and take the difference between them. It looks like we got chlorine is 3.16 and boron is 2.04. So that gets us 1.12, okay? So that means this is polar. It falls within that range. Now, the question is, which one is more polar? It's going to be chlorine, right? It has a higher electronegativity value. So that's going to help us when we're drawing these dipole arrows, because what you do is you draw a plus sign on the less electronegative atom, okay? And then what you do is you draw an arrow towards the more electronegative atom. This is kind of a funky arrow, but usually you draw them like this, okay? Like this. All right, and that would be a dipole arrow. Let me actually redraw this one. It's kind of bothering me. Okay, so you draw a dipole just like that, okay? So what that means is this is indicating that the bond itself is polar. Now, that does not necessarily mean that the molecule itself is polar. The molecule itself will be polar, one, if the bonds are electronegative, actually, or the bonds are, let me write these rules here, because it's just going to be really helpful. So, one, molecules will be polar if the bonds are polar, and there's asymmetry, okay? And I'll talk about what that looks like here in a second. Asymmetry, or where the vectors of the dipoles do not cancel out. So if we look at this really quick, this Lewis structure with the dipoles, these dipoles act as vectors, okay? If you've taken physics, vector is just a direction with magnitude, okay? All this is indicating that this dipole has some sort of, that has a direction in this direction upward, and that has some sort of magnitude involved with it, magnitude of electron density in this case, okay? Now, this vector here, the one right here that's pointing upward, is actually canceled out by the sum of these vectors downward, okay? Even though these are both pointing to the left and to the right downward, sort of, they actually add to go downward as well, and it actually always will match the opposite direction, because it's like exactly half of each of those vectors, which equals one full vector, okay? And that works for every direction. And so what ends up happening is all these dipoles, even though they exist, end up canceling each other out in terms of overall polarity of the molecule. So this is actually a nonpolar molecule, okay? Nonpolar. And so we don't need to draw a dipole arrow of the molecule's polarity because it's a nonpolar molecule, okay? So that's kind of how you're going to want to think of it. When you have shapes like these, okay, if you ever have a lone pair, actually, let me just circle this column instead, okay? That column will always be symmetrical, okay? Meaning, if you, when you have only atoms bound in these places, the greener atoms, and then these would be the electrons, the lone pairs, it's always going to be symmetrical, okay? When you have lone pairs, they kind of jack everything up, and usually, for the most part, lone pairs cause molecules to be polar because they by default create asymmetry, okay? So if we look at bent, notice that there would be, let's say a vector here and a vector here. They don't cancel out each other, right? Or a vector down here, a vector down here, a vector down here. They don't cancel out. And you can kind of see that with every example. The only examples where this is actually not the case is in the following. Linear, okay? This happens when you have a steric number of 5 and there's 3 lone pairs. They just sit around this equatorial axis. And then you only have a vector up and a vector down, so they cancel out. Okay, square planar. Okay, and then another linear. This one we actually don't cover in this class, so it's really only 2 other examples. And then we got square planar here. Sorry, not square. Sorry, I thought I said square planar. We got square planar right here and linear right here. Okay, those are the only other 2 examples that will end up being symmetrical. So actually, let me highlight. I'm going to put symmetrical in one color and then asymmetrical in all the other colors. So here we've got symmetrical will be in orange here. So I'm going to put these guys. Okay, here's my symmetrical atoms here. Okay, oops, let me erase this. There we go. Okay, those are symmetrical. Now asymmetrical, I'll put it in purple here. Okay, these are all asymmetrical. Whoa. So you'll just have to kind of memorize these shapes as well, along with the angles. They become more intuitive as you practice. But for the most part, this is just going to be straight memorization, okay? So, in this case, let's just do the shape really quick. All you have to do is figure out what's called the steric number, okay? Steric number, that's this number right here, okay? Now, the steric number, you'll count as either a lone pair or a bond. And in this case, in boron, we've got 3 bonds, okay? And that means the steric number is 3, and we don't have any lone pairs, okay? So there are 0 lone pairs, which means I would call this a trigonal planar molecule. So they didn't ask us for that here in this case, but just kind of so you get a feel for it, we're going to be doing this a lot later in this problem set, a lot more often, so that you'll get a hang of this. All right, second one here is SOCl2. This is used a lot in organic chemistry. It's a very good, it does a lot of good reactions for us, but here's the Lewis structure. Okay. And then like I said, we could have gone through all of that, but through drawing a Lewis structure, but I've done a lot of those in previous videos. Okay, so what we're gonna do, actually, let me leave that up here. So what I got to figure out first is, are the bonds polar? Okay, so now I'm gonna go back down here to my electronegativity chart. Okay, I'm gonna look at sulfur 2.58. And oxygen 3.44. Okay, so between oxygen and sulfur, as long as you can tell that that's going to be above 0.4, which I can tell, I'm actually just going to I don't even need to know the actual value. I just know that there's going to be a dipole pointing up towards oxygen, okay? Same with chlorine, except for chlorine, it looks like, let's see, 3.16 minus 2.58. That would end up being, yep, a little bit greater than 0.5, okay? So, or a little bit less than 0.5, but we're going to call that polar, okay? So we're going to go down here like this. All right, so that means that all the bonds are polar. Now we have to determine whether this, so we've determined the bonds are polar. Now we have to determine if it's asymmetrical. And notice there's a lone pair. That's almost always an indicator for there to be asymmetry, okay? But let's just double check just in case. So we've got a steric number of 4, right? We've got a lone pair, we've got a bond here, and a bond here. So the steric number is 4, which means my electron pair geometry is tetrahedral, but I have one lone pair, which makes this trigonal pyramidal, okay? Now, trigonal pyramidal is going to be asymmetrical. So this is not a polar molecule, polar. So this is going to be, this was nonpolar, and this is polar. Okay, now to determine where the direction is, it's kind of hard the way I've shown it because this is not in 3D. So I'm going to redraw this so you can see where the dipole is. So in a tetrahedral formation, you always have 2 on the plane. So what I'm going to do is I'm going to put sulfur right here. I'm going to put my lone pair up here, and then I'm going to put my oxygen on the plane of the page. And then what we do is we're going to have 1 going into the page, which I'll put 1 chlorine here going into the page, and 1 chlorine coming out of the page. Okay, so hopefully you can kind of see this structure. We've got this lone pair on the top, and then it's kind of this trigonal pyramidal. Can you kind of see why we call this the trigonal pyramidal? It just kind of looks like a pyramid. So, what happens is I've got dipoles down this way, I've got a dipole down this way, and a dipole down this way. So overall, the dipole goes down like this, okay? It goes down. All right. I hope that was helpful. We're going to move on to number 2. We've kind of talked about this a little bit. Explain the difference between a polar bond and a polar molecule. Okay, a polar bond, you can have that electronegativity difference, right? We determined that these bonds were polar, right? Between boron and chlorine. However, we were not able to determine that these were that it was a polar molecule, right? So polar molecule has to do with the symmetry of the molecule. This has to do with the electronegativity differences between the 2 atoms that are bonding. Okay. All right. Letter B. Circle the stereoisomer that is more polar. Okay. So remember, these if you can tell, these are going to be cis and trans isomers. Now, what we did before is we cut this perpendicularly, said side 1, side 2. This is the biggest group on this side. This is the biggest group on that side. Then when we look across the bonds, this is a trans, okay, because they're on the opposite side of each other. We did this in the last video, so I'm just going to leave that to you. So it can be here, here. That's going to be on the same side. So this is going to be cis, okay? So now what we need to determine is based on the directions of the dipoles, whether which stereoisomer is going to be more polar. Now, if in the carbon to chlorine bond, you can see that there's going to be a difference of greater than 0.4, okay? It's going to be slightly greater, but enough that we're going to be like, okay, there's going to be a dipole here and a dipole here and a dipole here and a dipole here. Now, can you kind of tell, whoops, that kind of looked a little jacked up, kind of tell that these are going to kind of cancel out each other, right? It's going to be a lot less polar because we're pulling this direction, but we're also pulling almost equally in the opposite direction, okay? So they're going to kind of cancel out. So this is going to be the more polar molecule because these both have dipoles that actually end up adding up to an overall dipole going upwards this way. And there's nothing to cancel it out in the back here. So the cis molecule is going to be more polar, and that will almost always be the case, okay? Cis molecules are typically the more polar molecule just because of their shape. All right, last one for this video. Number 3, it says the shape of electrons around each individual atom can also be determined. Determine the electron geometry around each carbon in the molecule and estimate the bond angles. Okay, so electron pair geometry is different from molecular shape, okay, molecular geometry. They've specifically asked for the electron geometry, so that's what I'm going to give you. So all that really means is the electron pair geometry is really just what a molecular geometry would look like without lone pairs. That's all that really means, okay? So we're going to look at this. I'm going to label this carbon 1, carbon 2, carbon 3, and carbon 4. And then I'm going to put my answers up here, okay? So carbon 1 has a steric number of 1, 2, 3. It doesn't have any lone pairs. Okay, so I'm going to circle 3. Okay, when I get to 3, that's going to be a trigonal planar molecule. Okay, trigonal planar. Now, that will, as long as there are no lone pairs, I'm going to assume that the bond angle is also going to stay the same. So I'm going to put 120. The only times the bond angles change, okay, this is critical for the test. The only times that the bond angles will change is when you have lone pairs, okay? So in this case, let's look at the bent one really quick. It's got a steric number of 3 as well. However, electron pairs or electron lone pairs, they tend to push a little harder than regular bonds, okay? So actually push them down extra because they're not confined to more of a space. They kind of have this open space around them. And so they'll repel the bonds a little bit downward. So we actually say that this bond angle here will end up being less than 120, okay? All it is you put a less than sign in front of what the steric number's original bond angle value would have been, okay? So like if we looked at trigonal pyramidal, for example, I know that it should have been 109.5, but because there's a lone pair, I'm going to put less than 109.5, okay? So as long as you have these basic angles memorized, all you have to know is less than if there's any case where you have a lone pair. In this case of bent, this is one of the few where we actually put 2 less than signs because it's got 2 extra lone pairs that are actually pushing down extra hard on these 2. So we'd say less than 109.5. You don't actually have to know like the actual angle value for that. Okay, so really quick, number 2, we've still got a steric number 1, 2, 3 without any lone pairs, so it's going to be the same. I'm going to just put those quotes there to indicate that it's the same. Now, if we look at number 3, we've got a steric number 1, 2, 3, and 4. So if I look at steric number 4, I don't have any lone pairs, so I'm actually in the tetrahedral formation. Okay, and that means my bond angle would be 109.5. Okay, so that means that this let me rewrite this, that the number 3 carbon here, okay, is going to have this shape right here, right next to other carbons that have this shape. Okay, it looks kind of funky once you start to look at it in real life. There's actually models that you can look at online. It can show you what these actually look like. It's kind of interesting. Okay, last one, number 4. We've got a steric number of 1, 2, without any lone pairs. Okay, so I'm going to look at steric number of 2. That's linear, okay, linear, and that's going to be a 180-degree angle. So really, with these shapes, honestly, just remember the bases. So remember linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. I would even get a model set if you could, and kind of look at these in 3D to get an idea what these look like. And then once you figure out those, just focus on this group first. Once you've got those down, it's a lot easier to understand when you have lone pairs. Okay, so all you have to do is, like, let's say you have trigonal planar memorized. You take out one of these and you say, okay, that's a lone pair. But now that I don't look at this as part of the bond, I'm going to say, oh, that just looks bent. Okay, so it's a lot easier once you've been able to do that, to memorize the bases. All right, I'll see you in the next video.